All right, as we get into the last sections, I want you to take a moment to consider these two Corvettes. They're both 58 Corvettes. One of them is a souped up 58 Corvette. The other is just a classic. And notice beneath them, the pink one is 0 to 60 miles per hour in 4 seconds, while the teal one is 0 to 60 in 8 seconds. So what's this difference here? What does it mean to soup up a Corvette, right? Well, for one, the souped up one has a much higher acceleration, can go through the speed change in a smaller amount of time, where the classic takes, for the same speed change, takes a longer amount of time, so it's a smaller acceleration. But physically, what causes the difference in the accelerations? Well, if we think about each engine, they're doing the same amount of work in that they're going from 0 to 60 miles per hour. So they're going from 0 kinetic energy to however much kinetic energy they have with that 60 miles per hour, 1/2 mv squared. So they're doing the same amount of work, but the pink one is doing it in less time. So this is a concept that in cars is referred to as horsepower, where the pink one has much more horsepower than the teal one. That's what it means to soup it up, right? Give it more horsepower, more HP compared to the classic version. And so we see that more power means it takes less time to do the same amount of work. And this is very close to our physics definition. So the definition of average power in physics is the rate at which work is done. So you take the work and divide it by the time required to perform the work. So the souped up one is dividing by a smaller time, so it's more power. What are the units of power? Well, we look at the units for work, which are joules, and then we divide them by our units for time, which are seconds, and they come out to what units? Yes, that is exactly it. They come out to units of the watt. It's spelled W-A-T-T, not with an H in there. And it's abbreviated as a capital W. So this is our unit for power. Cool. So think of work over time, and that's power. More generally, I like to think of it, and our book will also use that the power is the change in energy over time, because we know that work is related to change in energy, right? Often like change in kinetic energy. And so the change in energy over time is our power. And here's a conversion factor. 1 horsepower is 550 foot-pounds per second, or 745.7 watts. So that's how you can go from watts to horsepower. And to give you some sense of watts, here are some human metabolic rates. So the rate at which humans can burn energy, right? A change in energy over time. So running 15 kilometers per hour, that's about 9 miles an hour, so that's a 6 or 7 minute mile, is 1,340 watts. That's how much energy you burn in a second, right? So you could multiply by a number of seconds and you would get the total amount of joules that have been burned, which you could convert to calories. That's all that this is giving you, right? Skiing, biking is significantly less, lower power rate, right? Walking, even lower, and even sleeping, there's still a metabolic rate, right? So even sleeping, you are still using energy in that moment. Another expression for power that's sometimes used is that the average power is the force times the velocity. So this comes from the definition of power being work over time. And if you plug in that work, assuming the force and the displacement are in the same direction, is force times the displacement over time. Displacement over time is a concept we've seen before, right? That's our velocity. So we're just plugging that in for S over T, and we get that the power is the force times the velocity, average velocity. So that one's not used as often, but it is an alternative way to calculate power. So this is an introduction to power, but we are not going to stop here. We're going to keep powering through the other sections as well. So 6.8, other forms of energy and the conservation of energy. The principle of conservation of energy overall is that energy can neither be created nor destroyed, but can only be converted from one form to another. So energy doesn't just magically appear or disappear. It's just always converted. So this is somewhat very similar to the principle of conservation of mechanical energy, which says the total mechanical energy remains constant, provided that the net work done by external non-conservative forces is zero. In this one, the total energy is still conserved, but not the mechanical energy. So the energy is converted from energy of motion, kinetic and potential both allow things to move, into less useful forms. So friction, for instance, takes away some of that mechanical energy, energy of motion, and dissipates it as heat, which is a generally less useful form of energy. But the overall energy stays the same. So that's a nifty thing to consider. The very last section, 6.9, is the work done by a variable force. So we've previously looked at the work done by a constant force, and 90% of the work that we consider will be done by a constant force. So you don't have to worry too much about that. You're going to think about this equation most of the time. But there are some cases where the force will vary depending on the displacement, like a bow, right? When you first start pulling the bow back, it's not too hard. And then it starts to get harder and harder. More and more force is required to pull that bow back, right? And that's what's shown here, that the force actually is increasing with displacement over time. So what we can do instead is we can approximate, like, okay, how much force in that direction is acting for this little displacement, and we can add up all the little bits. In other words, we can do a graphical approach and say, hey, if this is the force that is acting in the same direction as the displacement, as a function of the displacement, then if we can get the area under this curve, then we can figure out the work done. So what that involves is counting boxes that are under this curve and noting that each box has these dimensions of 9.0 newtons times 2.78 times 10 to the 2. So we plug that in here, right? 9.0 newtons times this displacement of 2.78 times 10 to the minus 2 meters. And then as long as each box is the same size, we can just multiply that by the number of boxes. So some of the boxes you'll have to approximate, right? If the line is going through them, you might say that's half of a box. So this is an approximation method. It's not exact, but it is a way that you can estimate the total amount of work done by this variable force. So it's another useful method available to you. And with that, we have completed chapter 6, looking at work and energy.